The universe we see with our eyes seems simple and straightforward. Time ticks forward at the same rate for everyone, and a meter is always a meter long no matter where you are or how fast you're going. This is the world of our everyday experience, the world of common sense. But over a century ago, a young patent clerk named Albert Einstein imagined a universe that was far more bizarre and wonderful. His theory of relativity completely changed our understanding of the most fundamental things we thought we knew: space and time. He showed us that they are not fixed and absolute, but are instead flexible, stretching and squeezing depending on your motion and the force of gravity. This new vision of the cosmos brought with it a series of fascinating puzzles, ideas that seem to break the rules of logic. We call them paradoxes. These aren't just clever riddles, they are profound thought experiments that push the boundaries of our intuition and reveal the true nature of reality. They challenge us to let go of our earthbound assumptions and embrace a universe where two people can experience time passing differently, where the order of events can depend on who is watching, and where the very fabric of space can be curved. These paradoxes are our guides, leading us on a journey into the mind-bending heart of Einstein's universe. Exploring these paradoxes is like learning a new language for describing reality. At first, the concepts feel foreign and impossible to grasp, much like trying to imagine a new color you have never seen. But as we walk through each puzzle, one step at a time, the strange new rules begin to make sense. We start to see how time dilation, length contraction, and the relativity of simultaneity are not contradictions but are necessary parts of a single, consistent, and beautiful cosmic tapestry. The paradoxes are not flaws in the theory. They are the very features that show us how deeply interconnected space and time truly are. In this exploration, we will venture into some of the most famous of these relativistic puzzles. We will travel with a twin on a high-speed journey to the stars, ride a train that seems both too long and just right for a tunnel, and even contemplate how your evening walk could change the meaning of now for an alien civilization, millions of light-years away. Each paradox is a doorway to a deeper appreciation of the cosmos. So, prepare to have your mind bent and your sense of reality expanded. The journey begins now, into a universe that is not only stranger than we imagine, but stranger than we can imagine. Imagine two identical twins. Let's call them Stella and Tara. On their 30th birthday, Stella becomes an astronaut and embarks on an incredible journey to a distant star system. Her spaceship is a marvel of technology, capable of traveling at nearly the speed of light. Tara, on the other hand, chooses to stay home on Earth, living her life as usual. Stella's mission is a round trip. She will travel to the star, turn around, and fly back home. From Tara's perspective on Earth, the entire journey takes many years. She watches the seasons change, celebrates birthdays, and grows older, always waiting for her sister's return from the vast darkness of space. Finally, the day arrives. Stella's spaceship lands back on Earth. As the hatch opens, Tara, now an old woman, rushes forward to greet her sister. But the person who steps out is not old at all. Stella looks almost exactly the same as the day she left. She has aged only a few years, while decades have passed for Tara on Earth. This is the heart of the twin paradox. How can two twins, born on the same day, now have such a massive age difference? It seems impossible, a direct contradiction. Which twins' experience of time is the correct one? The answer, according to Einstein, is that both are correct from their own points of view. The solution lies in a key part of Einstein's theory called time dilation. This principle states that for an object moving at very high speeds, time itself slows down. From Tara's perspective on Earth, she saw her sister's clock and her biological processes ticking much more slowly as Stella zoomed through space. For every year that passed in Stella's spaceship, many more years went by on Earth. This isn't just a trick of perception, it's a real, physical effect. Stella genuinely experienced less time passing. But you might ask, from Stella's point of view, wasn't it Earth that was moving away from her at high speed? Shouldn't she see Tara aging more slowly? This is where the paradox part seems to get tricky, but there's a crucial difference between the two twins' journeys. Tara stayed in one place, in a single, steady frame of reference. Stella, however, did not. To complete her round trip, she had to accelerate to get up to speed, decelerate to stop at the distant star, turn around and then accelerate and decelerate again to return to Earth. This process of acceleration is what breaks the symmetry. Stella is the one who undergoes a change in her motion, switching reference frames. It is this acceleration that makes her the traveling twin in an absolute sense, and therefore, she is the one who experiences the dramatic effects of time dilation and returns younger than her earthbound sister. The idea that time can run at different rates for different people might sound like something straight out of science fiction, a concept confined to thought experiments about twins and spaceships. You might think it has no bearing on our day-to-day lives here on the solid ground of Earth. But you would be mistaken. In fact, many of us use a practical application of relativity every single day without even realizing it. If you have ever used a GPS on your phone or in your car to find the quickest route to a restaurant or navigate an unfamiliar city, you have personally witnessed the effects of Einstein's theories in action, working silently in the background. The Global Positioning System, or GPS, is a network of about 30 satellites orbiting high above our planet. Each of these satellites carries an incredibly precise atomic clock. To figure out your location, your GPS receiver on the ground picks up signals from several of these satellites. By measuring the exact time it takes for the signals to travel from the satellite to you, the receiver can calculate its distance from each one. With signals from at least 4 satellites, it can triangulate your exact position on the globe with remarkable accuracy. But for this system to work, the clocks on the satellites and the clocks on the ground must be perfectly synchronized, and that's where relativity comes in. There are 2 relativistic effects that mess with the clocks on those GPS satellites. First, because the satellites are moving at high speeds, about 14,000 kilometers per hour, special relativity's time dilation comes into play. Just like the traveling twin, their clocks tick slightly slower than the clocks on Earth's surface. This effect alone would cause them to lose about 7 microseconds every day. Second, and more significantly, is an effect from Einstein's theory of general relativity. This theory tells us that gravity also affects time. Clocks run slower in stronger gravitational fields. Since the satellites are far above Earth, they experience weaker gravity, causing their clocks to tick slightly faster than ours by about 45 microseconds per day. When you combine these 2 effects, the net result is that the clocks on GPS satellites run ahead of Earth-based clocks by about 38 microseconds, 45-7, every single day. This might sound like a tiny, insignificant amount of time, but in the world of high-precision navigation, it's a colossal error. Light travels about 300 meters in a single microsecond. If engineers didn't account for this relativistic time difference, GPS navigation errors would accumulate at a rate of over 10 kilometers every day. Your phone would tell you that you're miles away from where you actually are. So, engineers deliberately designed the satellite clocks to run a tiny bit slower, perfectly canceling out the effects of relativity and keeping us all on the right path. One of the most foundational and mind-bending ideas in all of physics is also one of the simplest to state. The speed of light in a vacuum is constant for all observers. It doesn't matter how fast you are moving or in what direction, you will always measure the speed of a beam of light to be exactly the same, about 299,792 kilometers per second. This sounds completely counterintuitive to our everyday experience. If you are driving on a highway at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the side of the road would see the ball moving at 120 kilometers per hour. Speeds add up. It's simple. It's common sense. But light doesn't play by these rules. Imagine you're on a futuristic train, a light train, that is traveling at half the speed of light. You turn on a flashlight and point it toward the front of the train. From your perspective inside the train car, you would measure the light from your flashlight moving away from you at, of course, the speed of light. But what about a person standing on a platform watching your train zoom by? Common sense would suggest they should see the light moving at the speed of the train plus the speed of the flashlight beam, 1.5 times the speed of light. But they don't. Incredibly, they also measure the flashlight beam's speed as exactly the speed of light. This is not a paradox in the sense of a contradiction, but a fundamental principle of the universe. It is the second postulate of Einstein's special relativity, and it forces us to reconsider everything we thought we knew about space and time. If the speed of light must remain constant for both the person on the train and the person on the platform, then something else must be changing to make the math work out. That something else is space and time themselves. For the observer on the platform, time on the fast-moving train must be ticking more slowly, time dilation, and the train itself must appear shorter in the direction of motion. length contraction. These two effects, time dilation and length contraction, are not just mathematical tricks. They are real physical consequences required to keep the speed of light constant for everyone, everywhere. The universe conspires, stretching time and shrinking space in just the right ways to ensure that no one can ever measure light moving faster or slower than its ultimate speed limit. This constancy is the bedrock upon which relativity is built. It means there is no absolute time and no absolute space. Both are relative to the observer's motion. The only thing that is absolute in the cosmos is the speed of light. Let's return to our futuristic, high-speed train. This time, we have a puzzle involving a train and a tunnel. When they are both at rest, the train and the tunnel are measured to be exactly the same length. Now, the train starts moving at a very high speed, approaching the speed of light as it heads toward the tunnel. An observer, let's call him the station master, is standing on the ground beside the tracks. From his perspective, the moving train undergoes length contraction. It appears to be significantly shorter than the tunnel. Therefore, there will be a brief moment when the entire shortened train is completely inside the tunnel. The station master could, in principle, close doors at both ends of the tunnel simultaneously, trapping the train inside. But now, let's switch to the perspective of a passenger sitting on the train. For her, the train is stationary. It's the tunnel that is rushing toward her at nearly the speed of light. From her point of view, it is the tunnel that is subject to length contraction. The tunnel appears to be much shorter than the train. Therefore, there is no possible way for the entire train to fit inside the shrunken tunnel at any single moment. If the station master tries to close both doors at once, the front of her train will smash through the exit door long before the rear of the train has even entered the entrance. So, who is right? Will the train fit, or will it be destroyed? Here we encounter another of Einstein's profound revelations, the relativity of simultaneity. The key to solving this paradox is the word simultaneously. For the station master on the ground, closing the entrance and exit doors at the exact same time is a perfectly straightforward concept. He can set up a device at the midpoint of the tunnel that sends a light signal to both doors, ensuring they shut at the same instant in his frame of reference. In his world, the train is trapped, but for the passenger on the moving train, those two events, the closing of the entrance door and the closing of the exit door, are not simultaneous. Because she is moving toward the signal that triggers the exit door and away from the signal that triggers the entrance door, she will see the exit door close before the entrance door does. From her perspective, the station master's plan unfolds like this. First, the exit door closes and then immediately reopens, just as the front of the train reaches it, allowing it to pass through safely. Only after the entire train has gone through the tunnel does the entrance door finally close behind it. Both observers are correct in their own reference frames. The train fits for the station master, and it doesn't fit for the passenger, all because the concept of at the same time is not universal. Imagine a perfectly flat, rigid disc, like a spinning record player, but one that can be spun up to speeds approaching the speed of light. Now let's think about its geometry. When the disc is at rest, we can measure its circumference and its radius. We know from basic mathematics that the circumference is equal to 2 times pi times the radius, or c equals 2 pi r. This is a fundamental rule of the flat Euclidean geometry we all learned in school. But what happens when we spin the disc at relativistic speeds? This is the essence of the Relativity Paradox, a puzzle that bridges the gap between special and general relativity. An observer standing still and watching the disk spin would see something strange. The edge of the disk, its circumference, is moving at a very high velocity. According to special relativity, any length that is moving in its direction of motion should experience length contraction. Therefore, the observer would measure the circumference of the spinning disk to be shorter than it was when it was at rest. However, the radius of the disk, which extends from the center to the edge, is moving perpendicular to the direction of the spin. Its length is not in the direction of motion, so it does not contract. The radius remains the same. This leads to a baffling conclusion. We have a disk whose radius has not changed, but whose circumference has shrunk. If we were to now use our measurements of this spinning disk to calculate pi, we would find that the circumference divided by twice the radius, the diameter, is no longer equal to the familiar 3.14159, and so on. It would be a smaller number. Does this mean that motion can change the value of a fundamental mathematical constant like pi? This seems absurd. The paradox highlights a deep tension in applying the rules of special relativity to rotating, and therefore accelerating, reference frames. The resolution to this paradox is profound and points directly toward Einstein's general theory of relativity. The paradox arises from the faulty assumption that the geometry of the spinning disk remains the flat, Euclidean geometry of our everyday world. Einstein realized that the effects of acceleration are indistinguishable from the effects of gravity. The intense acceleration, felt at the edge of the disk, actually curves the fabric of space-time itself. In this curved, non-Euclidean space, the old rules like c equals 2 pi r no longer apply. The paradox isn't a paradox at all. It's a demonstration that space is not just a passive, empty stage. It is a dynamic entity that can be bent and warped by motion and gravity. We have a powerful, intuitive sense of the present moment. We feel that now is a universal instant that we all share, a single slice of time that encompasses the entire cosmos. You are reading this sentence now. At this same now, someone across the world is sleeping. And at this very same now, something is happening in the Andromeda Galaxy, our closest galactic neighbor, located 2.5 million light-years away. Perhaps a star is exploding, or a hypothetical alien civilization is launching a fleet of ships. This idea of a universal now seems like the most basic fact of existence, but relativity tells us this comforting idea is an illusion. This brings us to the Andromeda Paradox, also known as the Riddick-Putnam-Penrose argument. It takes the relativity of simultaneity to its cosmic extreme. Imagine two people, Alice and Bob, sitting on a park bench. Then Alice stands up and starts walking away from Bob. Bob remains seated. Because Alice is now in motion. Relative to Bob, her plane of simultaneity, her personal slice of what constitutes now across the universe, has tilted ever so slightly compared to Bob's. For events happening nearby, this tilt is imperceptibly small and makes no difference. But when you project that tiny tilt across the vast 2.5 million light-year distance to the Andromeda Galaxy, the difference becomes enormous. Let's say that in Bob's stationary frame of reference, the aliens in Andromeda are just now deciding whether or not to launch their invasion fleet. His now contains their moment of decision. But for Alice, who is walking at a gentle pace in one direction, her tilted plane of now might slice through Andromeda's timeline, a full day into the future. In her present moment, the invasion fleet has already been flying toward us for 24 hours. If another person, Carol, were walking in the opposite direction, her plane of simultaneity would be tilted the other way, slicing through Andromeda's past. In her now, the aliens haven't even met to discuss the invasion yet. The mind-boggling conclusion is that all three perspectives are equally valid. There is no single, true, now. Whether the alien invasion is in the future, the present, or the past depends entirely on your motion. This paradox strongly suggests a block universe model of reality, where the past, present, and future all exist simultaneously and eternally. Time doesn't so much flow as it is simply there, and our consciousness just experiences it slice by slice, with the angle of that slice determined by our movement through space. Your simple walk in the park redefines the present moment for an entire galaxy. High in Earth's upper atmosphere, cosmic rays, energetic particles from deep space, collide with air molecules, creating a shower of secondary particles. Among these are tiny unstable particles called muons. Muons are like heavy electrons, and they have a very short lifespan. When at rest, a muon will decay into other particles in an average of just 2.2 microseconds. That's 2.2 millionths of a second. Even though they are created at high altitudes and travel toward the ground at nearly the speed of light, a simple calculation shows they shouldn't make it. In 2.2 microseconds, even at light speed, a muon could only travel about 660 meters, yet Earth's atmosphere is many kilometers thick. And yet, we detect these muons on the ground all the time. They rain down upon us constantly. How is this possible? How can a particle with such a fleeting existence survive a journey that should take much longer than its own lifespan? This puzzle, the muon decay paradox, provides one of the most direct and compelling real-world confirmations of Einstein's special relativity. The solution depends entirely on whose perspective you choose to take. Ours, here on Earth, or the muons, as it hurtles through the atmosphere. Both perspectives give the correct answer, perfectly demonstrating the consistency of relativity. Let's first look at things from our frame of reference on Earth. We see the muon traveling at an incredible speed, about 99.5% the speed of light. According to special relativity, an object's internal clock slows down the faster it moves. From our perspective, the muon's life clock is ticking much more slowly than a stationary muon's clock would. This time dilation effect extends its average lifespan by a significant factor. Instead of decaying in 2.2 microseconds of our time, its life is stretched out, giving it more than enough time to complete the long journey from the upper atmosphere down to the detectors on the surface before it decays. Now, let's switch to the muon's point of view. From its perspective, it is at rest, and the Earth's atmosphere is rushing up to meet it at 99.5% the speed of light. In its own frame of reference, its lifespan is just the normal 2.2 microseconds. Time dilation isn't a factor for its own clock. So how does it survive? From the muon's perspective, the distance it needs to travel is subject to length contraction. The entire thickness of Earth's atmosphere, which is moving toward it, is drastically shrunk in the direction of motion. The journey that we measure as many kilometers long appears to the muon as only a few hundred meters. This much shorter distance is easily covered within its brief 2.2 microsecond lifespan. Both explanations are correct, and both lead to the same result. The muon makes it to the ground. We have journeyed through a land of paradox, from twins who age at different rates to trains that are simultaneously too long and just right for a tunnel. We have seen how the simple act of walking can redefine the present moment for a distant galaxy, and how tiny particles can live longer lives just by moving fast. Each of these puzzles, the twin paradox, the train and tunnel, the muon's journey, seemed at first to be an impossible contradiction, a place where the laws of physics break down. Yet, in every case, the solution was not to dismiss the puzzle, but to embrace a deeper, more profound understanding of the universe. These paradoxes are not failures of science, they are its greatest triumphs. They are the signposts that tell us when our common sense has reached its limit and a new, more powerful idea is needed. Einstein's relativity provided that new idea, showing us that space and time are not the rigid, unchanging backdrop we once thought they were. Instead, they form a dynamic, interwoven fabric, space-time, that can stretch, shrink, and curve in response to motion and gravity. The paradoxes dissolve once we accept that measurements of time, distance, and even simultaneity are not absolute but are relative to the observer. The real-world consequences of these ideas are all around us, most notably in the GPS technology that guides our travels. This is not just abstract theory. It is a practical description of the world we inhabit. Relativity has passed every experimental test we have thrown at it for over a century, from observing the bending of starlight around the sun to detecting the faint whispers of gravitational waves from colliding black holes. It reveals a cosmos that is far more wondrous, strange, and interconnected than our ancestors could have ever dreamed. It tells us that reality itself is a matter of perspective. Ultimately, these mind-bending concepts teach us a lesson in humility. They remind us that our everyday experience is just one limited slice of a much grander and more complex reality. The universe does not owe us simplicity. It does not have to conform to our intuitions, which were forged on a planet where things move slowly and gravity is relatively weak. But through the patient, persistent, and imaginative process of science, we can begin to peel back the layers of illusion and catch a glimpse of the true underlying rules of the cosmos. The world is stranger than we thought, but through science, we have the tools to make sense of the strangeness.